together 2025. The next speaker is going to be Floris van Doorn, and he's going to talk about he's going to give a progress report on the Carleson project.
Thank you very much. Yeah. Yes, so I think many of you have seen the Carleson project around on Zulip, but maybe not all of you have looked a little bit deeper into it. So I will give some overview of like what the Carleson project is, what we've done so far, and I want to talk about also then some of the design decisions, like some like actual math formalization design that we've learned from the project, some lessons that we can use for other projects and so on. So I'll not start with the mathematical content, but I'll get to that a bit later in the talk. So let's start with a little bit of a timeline. And of course, it's a very, very selective timeline where, so the Carleson theorem is a theorem from 1966, proven by Leonard Carleson, and it's in Fourier analysis. So it talks about like the Fourier transform and when it converges in some way. I'll get to the precise statement later. And then it was extended in 1968 by mathematician Hunt. And the next thing that is relevant for us, although over the years, like there's been many generalizations of like how you can generalize the Fourier transform and so on. But in 2023, the Bonn harmonic analysis group under led by Christoph Thiele has like proven in a traditional way like a generalized version of this Carleson theorem. And then in summer of 2023, I also joined the Bonn University. And so we started about, can we do some kind of formalization project together? And quite quickly we came to the Carleson theorem is actually a really nice result for this because it was like recent research that they've done, and it's like generalization of like this traditional result in harmonic analysis that is actually really, really hard to prove, like has a really notoriously complicated proof. So at first what we did, so they already produced like a 30-page paper, like a traditional math paper, of the results. It was still internal, it's not published. And also not made public on archive. And I just started to sit down a bit naively and just wrote down some definitions, wrote down the statement, and tried to start proving like some of the basic lemmas. And we realized really quickly this was not going to work well in a scalable way. So the hope was also that some of the harmonic analysis people would learn lean and join. But of course, we all know that learning lean takes quite some time and it's quite a time investment, and so there was like a good effort was being made, but that was definitely going slow. And on the other hand, when reading the paper, there were the usual shortcuts in a mathematical paper where like things that were clear to experts in harmonic analysis were not clear to me at all. And so I had to continuously ask questions like, oh, how does this proof go? What is the next step? Does this actually work? Like what is the actually details? And so we tried this a bit, but it didn't really go very well. And so then we decided what maybe I could have known from the start is that we should write like a very detailed blueprint, which like Patrick Massot has already done for the Sphere version project, and many projects are now using. So that happened a few months later, where really the harmonic analysis group sat down and write like a very careful blueprint, fixed some mistakes, polished some, or like smoothened some parts of the proof. And that took them like quite a few months, and it had minimal input for me. I told them like what is roughly in mathlib. So like we have measure theory, like that's fine. We have the definition of the Fourier transform, but actually not that much more. And so based on that, they wrote like this very nice blueprint that is like really, really detailed. Um, And then, so in June, I announced sort of this collaborative project to like formalize this blueprint. And actually, the reaction from the Lean community was really good. Like, quite a few people joined and started claiming some lemmas that I had already formalized the statement and some of the definitions. And there were quite a few like low-hanging fruits uh, targets that yeah, we got like a very good start this way by proving like two chapters, like quite most of two chapters quite quickly of the blueprint. And so 3 months later, I with some caveats announced we're quote unquote 50% done, where it meant we had formalized 50% of the lemmas. And there were some caveats, like these were probably um, like the easier of the easier half of the lemmas. And actually I already had a bachelor student that already started a few months earlier and doing some formalization. But yeah, the progress was really good. So since September the progress is still going quite well. Like it's still going on and like there's still a really nice amount of contributions. But it is slowing down, and I think that is partially that the results are getting harder, and partially that I mean people are teaching, and the June to September period was mostly like summer break where people have maybe a bit more time to do work on Lean. This is what the current dependency graph looks like. So of course you cannot read any of the individual nodes, but you can roughly see a fraction of green nodes. So it's a bit more than half of the nodes are green. And to give you a bit of an idea of the proof, so in the top right is the proof of this general result, the generalization that is sort of the main result, which is here in red. And then the green parts are sort of are the proof of deriving sort of the classical 1966 results from this generalization. Um, yeah, so that's is sort of like a graphical idea of the proof. Um, yeah, I mentioned many of this already. So I formalized most of the statement, not all of them, but and then contributors usually formalize the proofs. And one thing that was interesting is that most people that contributed actually did not have a background in Fourier analysis. And still, like many of the proofs were written in such a way that they could be formalized by like outsiders, especially the somewhat easier lemmas. And so here is a list of yeah co-authors slash contributors. So the blueprint was mostly written by the Bond harmonic analysis group, and then formalization. There's these are the main contributors to the formalization project. There's a few more that have made like one commit or something, but like it's really nice to get such a reception, and I'm really happy with everyone that contributed to this project. Um, so the blueprint, yeah, so the organization of this is via Zulip. So for maybe a next project, I'll use like the infrastructure that Pietro has set up for the equational theories project, where we use like GitHub projects, but now we're mostly coordinating via Zulip, and that actually works quite well. It requires a minimal amount of manual work for me, like assigning tasks to people, but yeah, it works quite well. So we coordinate things on Zulip, and then I get pull requests in the repository that I review. So the blueprint, so originally the proof was about a 30-page proof, and that became like 4 times as long. It became like a 120-page proof of this general result, the generalization of the Carleson theorem, and then there's additional 30 pages to derive the classical results from the generalization. So that is not completely straightforward, but those are mostly standard techniques. And then here's a list of some of the chapters of the blueprint. And so the blueprint is holding up like actually very well. Like there are like many contributors have noticed like small inconsistencies in proofs of individual lemmas. I think a few times we had to change the statement of a lemma because it wasn't quite right or it wasn't quite what we needed. But actually, like there's no big problems that we found in the blueprint. One thing that does happen quite a lot is a lot of the statements are like asymptotic estimates or something like this integral is bounded by some constant times something else, and there's a few mistakes in the constants and quite a few improvements of the constants during the formalization. Um, so yeah, one thing that is that I think is really nice is that if you're an experienced Lean user, you can really contribute to this, to like a project like this, even if you don't know the mathematics that well. If you don't know it completely, then it's quite then it is, I think, quite tricky. But even if you don't know it quite well, then it works well. One thing that is trickier is from a blue like going from the blueprint to like mathlib ready like generalizations of results. If you want to write a lemma in a like more proper generality, that is quite a bit trickier if you don't know the mathematics, because then you don't know how to like reformulate or generalize the results. And so for the main part of the proof, like the actual like technical meat of the proof, we actually do not follow mathlib standards. We just have like a proof that is just for this specific case, and we're not thinking about every individual lemma. Like how can we do this in the most generality? But then many of the ingredients in the proof, we're trying to do them really in like mathlib proper generality so that they can be upstreamed easily. And so here's a list of a few things that we have and we want to upstream. So to also get a lot of these ingredients into mathlib. So let me talk a little bit about the mathematical content. I already mentioned it's about Fourier analysis, and so the Fourier transform is important. So let me quickly show you what the Fourier transform of a function is. So you start with, say, an integrable function, and then you can define the Fourier transform as a new function. So often you think of f as a function, say in space, where the domain is sort of a spatial coordinate, and then the Fourier transform is a function in a frequency coordinate, and you like integrate over all space with respect to this parameter psi, which is the frequency. And of course, this has to do with sort of breaking up your function into like waves of different wavelengths, but I'll skip the sort of intuition on the Fourier transform in this talk, and I'll focus on one thing. What if f is not integrable? Because then, so then this integral here might not converge in general, like it doesn't converge absolutely. But you can, of course, still view this as an improper integral. So if your function is not integrable, but say locally integrable, then you can take this integral on like an interval from -r to r, and you can take the limit as r goes to infinity and see if that converges. And then for more functions, this will converge. But the one question that is very important is with what topology do you ask for this convergence? And so how this behaves depends very strongly on the topology you choose. So either you can choose pointwise convergence. So like for each psi, does this integral converge? Like does this integral exist, and then does it converge to a value? So that's pointwise convergence, or you can look at LP convergence. So you can look at this whole Fourier transform as a function, as an LP function. So with respect to the LP norm, which is just like integrating the function to the pth power. And this defines some normal functions, and you can look, does this this function um, define like an element of LP with respect to this LP norm? And with respect to say the L2 norm, things behave quite nicely. Because so if your function starts out as an L2 function, then the Fourier transform is well defined when you take this limit with respect to the L2 norm, and the Fourier transform is again in L2. So then you can also take the inverse Fourier transform, and you get that like the inverse Fourier transform is actually the inverse of the Fourier transform, which is good for terminology reasons. So for pointwise convergence, things get a bit trickier. And so if your function is like continuously differentiable, then things are very nice and you have the same result. But if your function is a bit is less smooth, like say it's only continuous, or maybe only like L2, then things are are quite a bit more complicated. But the Carleson theorem says what happens then with respect to pointwise convergence. So this is the Carleson-Hunt theorem. The Carleson theorem is just this result for p equals 2. And so this says if you have a function that is in LP for p strictly greater than 1 and at most 2, then you can look at this Fourier transform of f and then take the inverse Fourier transform. And then this inverse Fourier transform converges pointwise to your original function, at least for almost every x. So on a set of measure 0, it might still diverge or maybe converge to a different value. So that is the classical result of the Carleson theorem. That's like pointwise, this result also works, but it's a bit more tricky because you on a set of measure 0, it might still be wrong. And some remarks is that to give you some idea about why this is tricky. So like really you cannot remove this almost everywhere from the statement. So even if your function is say continuous and L2, then the limit might diverge from like some x on a set of measure 0. And actually you can also have some kind of converge statement that for every null set, like you can find some function that's where this inverse Fourier transform applied to the Fourier transform of your function diverges on that set of measure 0. So it really can go arbitrarily bad on sets of measure 0. And also I had this I said this f must be an LP for p strictly greater than 1. And that is because for L1 functions, it goes horribly wrong. It can go horribly wrong. There are L1 functions where just this expression diverges for all points x. And also, I now describe the situation in one variable. What if you have multiple variables? Then versions of the Carleson theorem also hold, but you have to be very careful about like the shape of integration. For example, if you integrate on a cube and let the cube go to infinity, then that will generally work. But as far as I know, if the shape is circle, then this is actually an open problem, whether this converges almost everywhere. So this gives you some glimpses at why this Carleson theorem is hard, because if you change it like a slightly bit, things can go disastrously wrong. So now next I want to give you a bit of a glimpse in like what direction this generalization is of the Carleson theorem. So what is the difference between the classical Carleson theorem of 1966 and then the 2023 result? And so the way that you prove the Carleson theorem is by studying the Carleson operator. So the Carleson operator is roughly this operator. So it takes a function and produces a new function. and it produces a function which looks a little bit like what you see in the Fourier transform. Like you have again this integral over f with the power of e, but then you have some kind of kernel in here as well. So here the kernel is like 1 over x minus y. And then the other difference is like you take the absolute value and then you take a supremum, and you take sort of a supremum over all possible constants here in the exponents. And so what all proofs of the Carleson theorem have in common is that they prove that this Carleson operator is bounded as a function from L2 to L2. So the L2 norm of this Carleson operator of your function is bounded by some constant times the L2 norm of your original function if you start with an L2 function. And so this is where all the work lies. And so this is what we are also generalizing. So there's a couple of ways you can generalize this Carleson operator. So first I mentioned that this is only roughly what the Carleson operator is. So what it means more precisely is that actually there's some problems with integration. Like when x minus y either goes to infinity or goes to 0, like there can be some problems with this integral. Because this 1 over x minus y might not be integral in those ranges. So actually you do the same trick as before, like you just integrate over a bounded interval here, say where x minus y is between R1 and R2. And then you take a supremum over all these R1 and R2s. So this is maybe more precisely what the Carleson operator is. And then you can, for example, generalize some aspects of this operator. So first of all, you can generalize this 1 over x minus y by some other kernel. So this sort of like some modification of your integral that's called a kernel, and you can generalize it by something so-called an arbitrary Calderon-Zygmunt kernel, which is a binary function with like a list of properties that I won't show here, but so you can prove that this operator is bounded. So what we also do is that we change this exponent. So this was before like a linear function in y, it was just n times y, but you could generalize it to some collection of functions that again satisfy some properties, and is so-called a compatible collection of compatible functions. And these could, for example, be polynomials. Then you get something related to the polynomial Fourier transform, which is a thing being studied, or you can consider other kinds of functions. And then and so these are generalizations that have also been studied in the last decades. And so what is some well, actually these compatible functions is also partially new in this result. And the other thing is that we are generalizing this domain x, the domain of the function, which was the real numbers, to an arbitrary space X, which is a so-called doubling metric measure space. So it's a metric space and a measure space where you have this doubling condition. So the measure of a ball with radius 2r can be at most like a constant factor b, the measure of a ball of radius r. So this is for all x and r. And so in this setting is sort of the generalization of these results. And so in this setting, this operator is a bit too general to prove like outright that it's bounded. In some cases it's not. But so the main result that is proven is like you have some simpler operator, and if that is bounded, then this Carleson operator is also bounded. So this gives you some glimpse of the proof. And so here is the proof in lean. And I don't know if Patrick Massot is in the audience, but he already asked me this question. So if you look very carefully, there's this hypothesis that f is continuous here. Currently in the formalization, and in a few slides ago, I said f only had to be like L2 integrable or something, and that is actually a restriction that the current formalization has, but that I do want to generalize. So it holds. So currently, the blueprint proves this for continuous functions f, but this we will generalize this also to f that lie in L2. And so currently we're only doing this for the Fourier coefficient. So that's what this partial Fourier sum is, and we also want to do it for the Fourier transform. So there's a few different versions of the classical Carleson theorem, and we currently are only targeting one, but we want to also target the others. And then just to briefly flash the general result, this is the general result. And so there's like a kernel here and a set of compatible functions and like a boundedness condition, and then we get another boundedness condition. I don't want to go into details here. So I have 5 minutes left, so I want to end on um, some of the design decisions that we're using in this project. So um, one thing is working with LP spaces. So I mentioned a couple of times, oh, this is a bounded function from like LP to LQ or something. And this happens a lot in that analysis where you have like bounded linear functions or sometimes bounded sublinear functions. And this is actually quite annoying to work with in Lean. So these LP spaces are basically integrable functions that are quotiented by almost everywhere equality. And this is like a perfectly fine definition, but it's actually painful to work with. And that is because you still want to treat them as functions and you want to apply them to arguments. But if you have a function that is quotiented by almost every equality, like your application only almost everywhere makes sense. And so, for example, like the sum of two functions applied to an argument is not always the same as like the two individual functions applied to the arguments, because those are only like almost everywhere defined. And so this equality holds almost everywhere, and that's quite painful. So one thing that I think we're not the first one to notice, but it's much nicer to work just with actual functions, not with quotients. And so you say that your operators takes an actual function and returns an actual function, and then with the property that it's bounded with respect to these LP norms. So one other design decision is about the like working with the reals, the non-negative reals, and extended non-negative reals, because all three of them are important. Like the reals are of course important, like the extended non-negative reals, those are sort of the codomain of like measures and of Lebesgue integration, and so that's also important. And then the non-negative reals sit sort of in between and has like a nice coercion to both of them. And so many proofs you use like multiple of these, and you have casts between them, and it's actually quite a pain to like transition your result between these types. And so what we tried at the start of the Carleson project is just use R everywhere. Like all the measures we're using and all the integrals we're using actually will be finite anyway. And so this should not like we shouldn't need this extended non-negative reals because we shouldn't work with infinity anyway. And this will make our life much easier because we just work with R everywhere. This was not a good idea. It just made the problem worse. So it was just harder to work with these like measures and suprema and integration just as real numbers instead of within the extended non-negative real numbers. Because for example, if you have a supremum over real numbers, to prove basically anything about it, you need to show that like your set is bounded and like bounded above and non-empty. And so in the extended non-negative real numbers, you just get nice default values, even if your set of values is not bounded or empty. And Mavlib actually likes to work with these operations in the extended non-negative real number because Mavlib works in a generality where you do care about these. So there was also a bit of a mismatch with like Mavlib lemmas we wanted to use and what we needed in R. And some operations were actually infinite on, say, a set of measure 0. And so that also caused issues. And I think I'll just skip my last design decision because I'm running out of time. So in short, I wanted uh, to also work with operations nicely in that take values in extended non-negative real numbers that are actually infinite on a set of measure 0. And so there's this like nice new type class called enorm that is already part of Mapflit, but that needs to be incorporated further. So let me stop here.